Okay, welcome everyone to this afternoon RISE Data Science Seminar. It's our pleasure to have with us Alexis Bellot from Columbia University. So Alexis is currently a postdoctoral research scientist at Columbia, and he got his PhD degree in applied mathematics for University of Cambridge under the supervision of Professor Michaela van der Schaar. And his work focuses on causal inference, hypothesis testing, and applications with special interest to health. So without further ado, let's welcome all to Alexis to our seminar. And we are very excited to have you. Unfortunately, we couldn't make it in person, but we hope you enjoyed this virtual visit regardless. So please go ahead and thank you for joining us.
Thank you very much. Thank you for inviting me and also for taking an interest in my research and for today's talk in synthetic controls defined continuously in time. So as you said, I'm currently a postdoctoral researcher at Columbia University, but most of this work was done while at the University of Cambridge and at the Allen Turing Institute in collaboration with my then supervisor, Michaela. So to set the scene, okay, sorry, I was just trying to move the slides, but I think I got it. So imagine you've implemented a policy. For example, you're a country, you've lowered taxes in an attempt to encourage economic activity, or you're a different region and you're trying to introduce face masks to curb the spread of disease. So in this setting, you sit sometime in the future, you have observed some data, for example, GDP figures in your country or newly infected people, daily or weekly figures. And you had implemented this intervention in the past, and you're asking yourself whether, given the observed data, if this policy was really effective. And here effective is always relative to a counterfactual. So the expected behavior, your economic activity or new infections had you not performed the intervention at a past time. And it will also be interesting to, another point of comparison will also be different countries that are not affected by your intervention are going to be used as control units, in this case, marked in blue. So before going into methods, please allow me a small digression into exactly explaining what is meant by a counterfactual in this case, and what is meant also by an intervention, which is really the domain of causality, which, as you'll see, is maybe a little bit different from classical statistics. So the basic object that we work with in causality more generally, and that will help you to describe the fundamental reality of the world, is a structural causal model. That is really a set of 4 elements that you have to describe what's going on. You have a set of observed variables that are the relevant parts of the system that are explicitly modeled. You have a set of unobserved variables which are not explicitly modeled but are relevant in the system, and they may affect what you see, but these are things you don't necessarily get to observe. And then you have a set of functions or causal mechanisms that map your unobservables to your observed variables, right? So each instantiation of your unobserved variables mediated through these equations will give you a unique value for your observables. These are deterministic equations. And finally, within a larger population, each of these instantiations of you has a certain probability, which gives you probability distributions over these unobserved variables, right? So quite abstract at the moment, but in our example, it will be plausible to assume that what you observe are your time series data points of economic activity or the new daily or weekly infections. The set of unobservables will be all other variables that influence this system, but that you don't get to observe. You may say, for instance, that these unobserved variables are mediated by a factor model. And in this case, what is happening is that your observed economic activity, for example, is going to be a time-varying combinations of these unobserved factors. And also a little point on some notation that we'll be using is that for each particular instantiation will give you a particular value of ui that you can write in this way. So y of u is going to be equal to a specific instantiation of y. So these structural causal models are incredibly flexible. So you can think of them as data generating processes, and really they define a hierarchy or different levels of cognition, different quantities, statistical quantities that are going to be truly distinct. So perhaps most obviously, a structural causal model defines an observational distribution, right? Using our notation as before. You can group all the values of u that give you specific y when mediated through your causal mechanism. Each one is associated with a certain probability. And from this, you get a probability distribution over your observed variables, right? This is simply the natural course of events. Without touching the system, without doing anything to it, you collect data and you have a certain probability distribution. But of course, in practical problems, and in our case, we act in the system, and there's going to be a lot of different probability distributions that we can define. So you have a second level, which is the causal layer or the interventional layer, where instead of just passively observing the system, before any data collection, you intervene and change a particular feature of the model. Say you change some causal mechanism. For example, instead of letting people decide whether to wear a mask or not, you force everyone to do so. So, and with a similar mechanism, by sampling from our distribution of u and propagating that everything through this new causal mechanism, you get an interventional distribution. There's not necessarily any relationship between observational distribution and interventional distributions. These are really, I mean, they come from different models. And depending on the underlying structural causal models, they can be arbitrarily different. One important note is that on the associative layer, this is where most of statistics and machine learning sits. You have this underlying distribution over your observed data. You typically have access to some samples of it, and the problem is typically to recover some functional of the underlying distribution, say a conditional expectation or a conditional probability. Causal inference in this analogy is different. It's a form of cross-layer inference. You've given samples from your observational distribution, but you're actually interested in a different quantity, which is a functional from your interventional distribution, which you don't get to observe, right? And you can imagine a third layer, which is instead of considering a unique intervention, you consider multiple simultaneous interventions at the same time. And these are called counterfactuals. You can model jointly competing models of reality, right? And this is what you would do when you introspect, go into the past, and think about what would have happened had you acted differently. All right, so going back to our problem, and really what are the underlying structural models that justifies using something like synthetic controls. So there are other models that allow you to justify, and different proposals have been made, but I guess for the purposes of this presentation, it'll be enough to assume one particular candidate. And factor models are a popular underlying model for that people will use when thinking about synthetic controls. So it is exactly as we introduced previously. So each one of your observation is a time-varying combination of a set of unobserved factors. So before treatment at time capital T, you have both the treated unit of interest as well as your control units that arise from such a factor model, perhaps with a different set of unobserved factors. However, once you intervene into the system, you can imagine changing the underlying causal mechanism by adding some factor. adding some time varying element that will give you a different trajectory for your observed units, right? And what we're interested is, and we're really in the business of computing individual level treatment effects. So what is the difference between the observed data we have after intervention and what would have happened without? So here the superscript 0 really stands for the factor model that the behavior before intervention, right? And synthetic controls are really just a method for estimating these counterfactuals. But they do something, in my opinion, quite interesting, which instead of attempting to approximate the underlying factor model, like you would do in other time series models, perhaps using lagged values as predictors for the future, which synthetic controls don't do. Instead, they do something different, is that they rely on the regularity of the association between units over time. So let me explain this in more detail. So our counterfactual, or the behavior of the unit of unit 1 without treatment is simply going to be a linear combination of other units that haven't been exposed to treatment, right? Have a linear combination of control units. And this is used to approximate your counterfactual of interest. And if you're able to fit a good linear combinations and to really approximate the pre-treatment behavior of your unit 1, and you're able to do this on extended periods of time, then with the assumption of the underlying factor model, the only way to really do this is that you also match on the set of unobserved factors, which is something that will allow you to extrapolate into the future, right? So a first point to note is that the credibility of such synthetic controls will depend on pre-treatment fit. There's many different approaches that you can use to estimate your vector of coefficients W, but the validity of this theory will depend on the pre-treatment fit. And original authors of this proposal, they bound the treatment effect or bias in the treatment effect, making this rigorous and depending on how many periods you have before treatment to approximate your unit number 1. However, note that in this definition, all units are assumed to be observed at the same time points. So the picture is really a little bit different in traditional synthetic controls. Every one of your observations over time are done at the same time points. You only get to update the counterfactual whenever you have observed time points. And you don't have any information in between. You're not able to necessarily to compute counterfactuals if you don't have any observations from other units, let's say from other countries or from other regions. And therefore, I mean, for applications, let's say of public economic policy, this might be enough because there is a certain protocol for observation. But for examples in medicine or healthcare, where your units are patients and everyone is irregularly measured, most of the time, I mean, almost never at the same time, then this formalism starts to break down. And this is also where our contributions start. So what we say is that really a time series, you can really interpret it as measurements from an underlying continuous time processes. Perhaps not in all cases, but in many relevant applications, this is the underlying assumption, right? And as a continuous time process, perhaps described by differential equations, the problem shifts from approximating discrete time observations to really recovering a latent continuous time process explicitly. We're interested in a path rather than the observations themselves. And exactly. So the formalism changes a little bit. And the assumption here is also more general, is that instead of having observations at every moment in time or on a specific grid of time points, every unit can have its own set of observations, and a first step will be to try to reconstruct the underlying path from these observations. And what I find interesting in continuous time is that the interpretation of synthetic controls as a combination of control units can really be applied in a very straightforward manner when speaking in continuous time. So what we're doing is that instead of considering combinations of control observations themselves, we consider combinations of the infinitesimal variation of control paths over time. So in differential equations, typically the relevant quantity is not only the state of a given variable, but its change in an infinitesimal period of time. And so instead of talking about the state of variables, we can talk about the infinitesimal variation of these paths. And what this really means is some linear or nonlinear function, like the one you see on the slide. So the infinitesimal variation of the treated unit is simply going to be a linear and nonlinear combination of the infinitesimal variation of control paths, right? And our latent path in this case will be said to be a solution from an underlying control differential equation, which is a set of equation that has been studied quite a lot, not too much in the machine learning literature until very recently. It comes from a group in Oxford headed by Terry Lyons. You may be aware. They have a whole theory of underlying these kind of equations when they have good solutions. And it's something that with this formalism is also directly applicable to synthetic controls in continuous time. So for our application, we'll use a particular version of these control differential equations. And specifically, we'll say that our counterfactual is going to be the solution to such a control differential equation, which is given by this integral, where our bold uppercase y is just a set of control paths, right? Now defined as a function from time to some domain. So the picture we're working with changes also differently. So now, rather than updating our counterfactual whenever you have observations from your control units, you're updating it continuously in time, right? So at every moment in time, the variation in your control units is affecting your estimation of the counterfactual. Just by looking at this integral. In blue, these are the elements, the control units. So specifically, just to make sure this point is understood, as a function, it can be evaluated at any moment in time. But note that it does require that we compute these derivatives to be able to evaluate this integral. And so typically we require an approximation of the underlying path. So you can think as a cubic spline approximation, something where derivatives can be computed will typically be enough to have faithful derivatives and to have an estimate that makes sense. Now, this formalism is really fairly general. For example, instead of having the actual counterfactual path being driven by this control differential equation, you can introduce much more flexibility. For example, instead of having the path itself, have a representation of this path to be the solution to the control differential equation. For instance, you'd be evaluating integrals of this form. And here our latent state z can be higher dimensional, a dimension that you choose, and you'll be, so yes, you can think of a layer above that that is really, this latent state is really mediated by the controlled differential equation. And then you have a function g that projects the space of the counterfactual path into this latent space. And whenever you want to make predictions, you have a second function, for example, a neural network, that projects this latent space into the observation space. So there's, I guess you start having a lot of complexity when you think about, when you start introducing hidden states and so forth. But if you're familiar with recurrent neural networks, you can simply think of this kind of family of models as a continuous time generalization of recurrent neural networks, right? So not too simple, but at the same time, not too exotic. And also, this is, I guess, optional. You don't have to model a hidden state to get consistent results. But this is something that you can do. And if you expect your relevant combinations to be highly nonlinear, or you need to model very complex functions, then this is a viable alternative for you to implement. Now, one of the things that makes synthetic control so useful in practice is the fact that fit is really simple, and we've really been moving away from it. First, introducing integrals and then a hidden state. And we're kind of losing the simplicity of the fit. So we can no longer tell that a simple linear combinations of a few control units give us our counterfactual fits. So it's much harder to really understand what are the influential control units and how are they really affecting our estimation. So one of the things you can do to try to mitigate this this limitation is to introduce a diagonal matrix that is going to control the influence of control paths. So we can just extend our solution to introduce this matrix W. So you can see before evaluating these integrals, we can set, or we can learn these diagonal entries. Some of them are going to be 0, and so you're limiting the influence of control units on your fits. So this is in an attempt to encourage sparsity, for example. And such an approach is very useful because it gives you a rigorous way to enforce that only a few control units actually influence the fit. But at the same time, introducing this matrix W is not limiting the expressivity of the class of CDEs, of control differential equations, that you actually learn. And this is a result that is formalized in this proposition. And that is simply comparing two classes of functions. One is your original non-weighted control differential equations, where the path you're approximating is independent of some control units. And the second class of functions is the weighted CDEs, where the ith diagonal entries of this matrix W is 0. And essentially what we're showing is that these two classes of CDEs coincide. So we're not losing anything by introducing W in terms of fit or complexity of fit. But we're rigorously enforcing this independence, which may be desirable for interpretation. Now, for completeness, I briefly want to mention how you can actually fit these models. But here, there's nothing really new from our side. So there are now, by now, established techniques to learn this kind of differential equations that are parameterized by neural networks. And that started with a very popular paper called Neural ODEs. And so we're just reusing their inference mechanism to learn our parameters. And the procedure just has two big elements. One is an ODE solver, any one that you choose, to actually compute these integrals and get our forward trajectory in time. And then you define a loss function. For example, in our case, you want to be comparing the reconstructed signal, so our estimation, with the actual values of that you do observe pre-treatment. And on the other side, you want to encourage sparsity in our matrix W. Right? You can compute gradients of these losses, backpropagate, and update your parameters as you would with any other deep learning models. Okay, so this part concludes the description of the method, and I'm now going to talk briefly about some experiments I believe I have another 15 minutes, so hopefully, so yeah, I should be fine on time, but let me know if I'm getting close to finish. Now, by the end of 2009, most of you will probably remember Europe was at the beginning of a multi-year sovereign debt crisis. Right, so some Eurozone countries, many will say because of Eurozone membership, have become habituated to running a large current account deficit. So the balance of the current account balance is the difference between a country's imports and a country's exports. Or, sorry, the other way around, a country's exports and a country's imports. And having a deficit means that you're importing much more than you're exporting. And to close this gap, at least at that time, Eurozone countries, given the positive climate as well as really very favorable interest rates, started to borrow a lot of money to be able to fund this current account deficit, which is something that was thought to really aggravate the posterior sovereign debt crisis, because countries weren't able to borrow as much as they did before, but still had this liability. So at this point, you may ask, well, did the Eurozone really have an impact on the current account deficit of Eurozone countries, and specifically Spain, which together with Portugal, Italy, Greece, and others were one of the worst hits within Europe? And well, I mean, yes, let's so this is also something that you can really see quantitatively how on the bold dotted line you see the current account balance of Spain, and in lighter gray you see the current account balance of different countries. The euro was introduced in 1998, and you can see that from that point onwards, Spain really started to have an increasing deficit, right? And you can also notice that trajectories in general are fairly heterogeneous. So things change a lot over time. Countries don't necessarily have a fixed trend or even any strong, obvious similarity between different countries. So more specifically, the question is, would Spain's trajectory from 1998 to 2010 had been any different had they not joined the euro, right? And you can blame the euro for many things, but synthetic controls really give you a rigorous way to test this hypothesis. You can use control countries that did not adopt the euro as a pool of control states, and try to approximate Spain's behavior before treatment, extrapolating your estimates and seeing if there's really a gap between the Spain's current account deficit and what you estimate would have happened had they not joined the euro. So what I want to show you in this slide is over successive iterations, the fit that you get from continuous time synthetic controls. So this is going to be a small animation. On the leftmost plot, you have two things. You have first the observed trajectory in blue that you recognize from the previous slides, and then continuous time synthetic controls that are going to vary over time as you approximate the fits. Again, I'm pointing out that you're trying to approximate the fit before treatment, so before 1998. In the middle panel, you have the treatment effect, which is the difference between the approximated counterfactual, the synthetic control, and the observed trajectory. And on the rightmost plot, you can see the trajectories of control countries, which are countries from around the world, that did not adopt the euro or that were not affected by the eurozone. And as you expect, well, you can see that with successive iterations of the algorithm, you get closer and closer to Spain's trajectory before the introduction of the euro. And the idea is that anything after is your counterfactual or the expected behavior had you not joined the eurozone. And of course, there have been many other competing alternatives for synthetic controls, mostly in discrete time. And you can explicitly compare the fits between different methods to try to understand what is really the gain of a continuous time approach, and perhaps also a more flexible approach that was previously proposed. So the original synthetic control method was issued by Abadi in 2010. But there have been other proposals. For instance, to estimate your coefficients W in the original synthetic control formulation, you could use kernel mean matching. Try to match distribution in a kernel Hilbert space. You can also use a penalized approach. For instance, running an elastic net over with inputs your control observation and the output the pretreatment fit of the unit of interest. And you can also have matrix completion kind of approaches. And in this case, what we observe is that our proposal, which we call NCNC, is neural continuous synthetic controls, much more accurately or much more faithfully approximates the Spain's trajectory before treatment, and all other methods are a little bit further apart from what you do observe before treatments. And as I said before, anything that comes before is really the expected trajectory had the euro not been introduced. So in this case, our, if you like, economic conclusion is that the Spain's current account balance wouldn't have been as worse as it had with the eurozone, and all methods more or less agree. So we had introduced our matrix W in the fit to be able to investigate which ones of our pool of control units really influence the fit, and whether this matrix W can give us any insight into these countries. And it turns out that to some extent you can do so with synthetic controls in continuous time. So in this case, the 5 countries with a positive weight, so where its diagonal entry of our matrix W is positive, where Japan, Chile, Mexico, Hungary, and Sweden. We cannot tell exactly how these trajectories influence the synthetic control of Spain, because the functions are nonlinear, and so the impact will probably be nonlinear and complex. But it does hold that these selected influential countries are consistently chosen across different runs of the algorithm. So this is it is definitely not a proof, but it gives you some confidence that that at least the local optima that synthetic controls in continuous time is converging to is somewhat consistent, at least in the set of influential countries that are used to approximate synthetic controls in continuous time. Okay, this is the end of my presentation. Thank you very much for your attention.
Okay, thank you, Alexis, for the nice talk. Definitely many interesting ideas that are popping up. So The way we're gonna do the Q&A is that please raise your hand if you have a question, and then I can give you access to the mic so you can ask the question directly. So also you can write the question in the chat if you prefer. So please, yeah, so use the raise hand to let me know that you have a question. Maybe I can start with one which is about performance guarantees, right? So you draw some conclusions based on, let's say, some analysis that you did on this specific set of data, for example, the economy in Spain. And my question is about what sort of performance guarantees can you provide about these methods, or how you evaluate whether these are good or bad estimates or conclusions that you're drawing from this analysis.
Yeah, so I guess the original factor model presented by Abadi, this has a direct analog in continuous time. And if you force your control differential equations to be linear, then a lot of these results on the bounds of on the bias of the treatment effects, they would apply in continuous time as well. You have to be careful about the distribution of error terms, which is likely going to have some correlation across successive times, since this is a continuous time process. But with some assumptions, you can probably get back the bounds that were originally derived for discrete time synthetic controls. Now, going beyond, once you introduce nonlinear functions, we don't currently have any statistical guarantees on our approximations, and this, I guess, is a big open question if you want to be using this in practice. However, if you guide yourself by the principle that in introducing some linearity, trying to limit the number of parameters in your model, if you do get a better fit in terms of the pre-treatment performance, then and you don't have any strong discrepancies with the original methods, then you can probably get some insights from synthetic controls in continuous time, but no formal guarantees yet.
Okay, yeah, thank you. Yeah, so I think it seems that we have one question here in the Q&A, so I'll just read it, and it comes from Ginevra. So Ginevra asked if you could extend this approach beyond time series, and so she's talking about what about assuming some smoothness over space, or some graph for estimating or graphs for estimating your synthetic controls.
So do you mean if you have maybe additional data, covariates, or some kind of graph structure to describe each one of the units, if you could incorporate that information?
Yeah, so then maybe
synthetic controls are really very closely tied to the time series setting. So I don't know if it's really necessary, and perhaps you can have you can derive a similar model for different kind of underlying structural causal models, and you probably can. I don't know that it has been done, but it doesn't seem to me to be impossible, at least to explore such an approach. But I don't have a lot of insights into that question.
Cool. I'm Ginevra here. Oh, sorry, that is closed. My video can't turn on for some reason. So super cool talk. It was more kind of like, what if you want to look at controls kind of in space and or time? So for example, like different spatial locations should be similar to each other. So you can use those as kind of controls in the same way that you're using time series. This could be really useful for some things in kind of geopolitics at the more local level, understanding things like that. I'm wondering, I know you set this up as kind of a learning system for these with differential equations. Can you extend this to a spatial domain? Or you can think of it more broadly, like on a graph, where you've got some type of differential equation on a graph. And that I don't know exactly what I'm asking about, but I could see instances where you would want some type of control that has kind of some type of spatial or other continuity there.
Yeah. So you're saying that you have some additional information on the similarity between units over time and how to incorporate that prior in your fits. So this is something that, at least with the formalism I described, can maybe most straightforwardly be incorporated in W itself. So you can, so if you know that a small set of units are particularly relevant for your estimation, perhaps because they're close to your unit of interest in space, or because you have an underlying graph and you know that these are tightly linked with your counterfactual of interest, then this is something that you can incorporate in W. For instance, you can bias your matrix W to have higher values for these particular units, or penalize them less, which is one approach. Now, I think otherwise you'd have to move away a little bit from the description I gave, and think of something slightly different. I don't know how you could incorporate it. How you would incorporate it otherwise.
Okay, thank you. So is there any additional questions? You can raise your hand. And if that, then I might have another question, and I always ask this question, which is about scalability of the methods. So you mentioned that you're using this off-the-shelf ODE solver, neural solver, and then I'm wondering, for many of these economic or health-related problems, you might not have all the data as traditional like data science approaches, right? You don't have millions and millions of points. Maybe you have one data point per year, or things like that. So what are some of the issues with the scalability and say sample complexity of the methods that you're using?
Yeah, that's a good question. Well, actually for the example I described with Spain's current account balance, you only had 19 pre-treatment periods. So of course there's many choices behind the scenes into what neural networks you're using, what is the dimensionality of the latent spaces, and how many neurons, and so on. But with some good judgments, if your parameter spaces are not too large, even with small samples, you're able to learn something meaningful. I guess it's worth noting as well that everything I talked about is unit level. So if you had to estimate counterfactuals for a large number of units, say in a medical setting, then you'd have to be running this multiple times, once for each individual. And yeah, so perhaps in that case you wouldn't use something like this. As a comparison to linear methods, it is definitely much slower, but for in the paper, I think we had some comparisons, some runtime comparisons. I don't have them on the top of my head, but yes, I think all the scalability problems or runtime considerations that you have when you go from something linear to something more deep learning like apply to this method as well. Yeah.
Great, thank you. So it seems that there are no additional questions from the audience. So if that's it, then I'll stop recording now.